So our first speaker for this session will be Professor Elisabetta Farella. She's a lead researcher in the energy efficient embedded digital architecture, which is also pronounced as E3DA, right? That's the right. So it's she's the lead research there. Her main key topics are tinyML and efficient neural network and running AI on embedded devices. And what else? It's so long. I mean, she has so many accomplishments. But I'll just one more sentence is that Elisabetta also participate in many technical committees for conferences around the world. She was working in the University of Bologna with Luca Benini, and you have like mentions and co-author of more than 150 papers. So with that, please welcome Elisabetta.
Can you hear me? Yes, yes. Thank you for the organizer to have set up this very nice conference, which is completely well-centered in what we are doing at E3DA research unit that I had at Fondazione Bruno Kessler, which is a private public research center in the northern Italy, in Trento, near the mountains, near the Alps, and the Dolomites in particular. And yeah, this is my screen. Thank you. The work I present here is about our research on bringing intelligence as much as possible at the edge, as all of you are doing. And in particular, in this case, we target phase swapping. I will say something about this, but in particular, this is done within the framework of the Marvel European project, which is a project targeting multimodal analytics at the edge and very edge in a kind of smart city scenarios. So in this kind of context, what we have is that we suppose that there are several sensors in public areas around the cities, like, for example, surveillance cameras. The typical way they are used at present is that data are streamed from the camera cameras directly to an operator centers, where analysis of the images and the videos are done manually by an operator, which is very inefficient. So in this project, we are trying both to automatize this kind of process by using AI to identify events, meaningful events, and at the same time doing this as much as possible close to where the action happens. The first drawback of keeping the traditional way is that the data leaves the sensor, so they are prone to attacks, cyber attacks, data leakage, etc. So the two main goals that FBK is tackling in this project are bringing all the intelligence near at the edge, so adopting a privacy by design approach, because as you all know, bringing the intelligence at the edge means that what I send over the network are signatures, patterns, events, and information which is less sensitive instead of streaming directly the let's say the faces of people that you capture in a public environment. And we want to, in some cases, however, we need to stream anyway the data, because law enforcement agencies wants to visually inspect anyway what is happening. So they are not happy with just the event, there is a crowd in this place, there is a dangerous event over there, etc. So what we try to do is to anonymize, do a video anonymization, audio anonymization of data before sending them, streaming them to the central operation quarter. We want to do this not only by blurring faces, for example, but we want to do this preserving meaningful information for the law enforcement agency to understand what is happening. So, for example, aggressive expression, scared expression, and so on and so forth. So our goal is phase swapping and video anonymization at the edge. But for sure, this is not a trivial operation because it requires, differently from just classifying or identifying things in a scene, it requires to generate something, which is, for example, a fake face to put on the real face of the citizens. And so this is a task typically performed on high-performance computing platforms where I have no restriction in terms of power capabilities. How we want to tackle this to go back to the edge? The typical way is trying several different networks, reading the state of the art, finding the most compressed network, trying to tailor the network for our, to optimize as much as possible. So we explore different possibilities and see which is the one that matches better. This is a typical process that probably many of you have already done in your research. But what's the drawback of this is that I have to train several networks for my purposes, and somehow this is not repeatable over different hardware that I can choose. It's a time-consuming approach, of course, and of course, even if I get the goal, maybe I don't use exactly as much as resources I have available in my platform. It's suboptimal somehow, the result that I get. So we try to change the approach, not doing hardware constrained scaling, we call it hardware-aware scaling. So we want to start from the real resources that we have in our platform and find a mechanism, a process in which we directly target that platform. So we implemented this, this is somehow a one-shot design of neural networks. It targets the bigger possible network I can run on my final device, and it's portable on different hardware. So I don't have to train it for the specific, I take as input the parameters that I have in terms of resources, and I get the characteristic of my network. What is that? We call this Phinets. Is a family of networks that addresses backbones, because we started at the beginning with object recognition and tracking kind of task. It is, in fact, one of the main computational expensive blocks. And what we do mainly is having 3 parameters that are directly correlated with the RAM usage, the flash usage, and the number of operation, the operation count. This is the general architecture of our network. As you can see, is migrated from existing network like mobile net that were presented previously by other presenters. What we do here is parameterizing the number of filters, the number of channels, and so our network is optimized in terms of this T0, alpha, and beta, correspondingly from our input in terms of RAM usage that we want to target, MAC requirements that we want to target, and flash usage. More details can be found. I don't want to go in too much in detail of how Phinets works, because it's not the topic of this presentation, but you can find more details in our recent publication that is mentioned there. And there is also all the code on GitLab with the relevant explanation. What we want to do is not using Phinets, but modifying Phinets, because we want to address a generative model to go on the microcontroller. So here we make our life more complex, because of course this is a task that requires, as I already said, more computation. Here it's just put in evidence some numbers, some figures of the required parameters, number of parameters and MEC that are required for some standard gun, state-of-the-art gun, like Go gun, which has 93 million parameters, 280 gigamex, and cycle gun. Of course, there are many attempts to go down in terms of complexity. Some are cited in the paper that you can find there. But it's not enough. We go down 10 times or 20 times. It's not enough for our target. We want to target microcontrollers, so like, I don't know, an M4 or an F7, etc. So we looked into the structure of the gun, and what is the most critical part is that the convolutional block, are traditionally inefficient. So we look at that, and what we did is modifying the original architecture of our Phinets including a bilinear upsampling block, which enables us to substitute the convolution or transpose convolution, as you want to call them, leading to more than 85% parameter reduction and more than 95% less operation count. As you see, the structure is similar to the original Phinet. There's just this block more. So again, each of these blocks is regulated by your initial requirements. So I have my MEC, flash and RAM requirements. I map into A, alpha, T0, and beta, and this designs my network. We applied successfully at first this generative network to a style transfer kind of task with good result, targeting this consumer platform for geeks, let's say, which is a Kendryte K210, which has a RISC V dual core running at 400 megahertz, and keeping the overall power consumption less than 300 milliwatt, to be precise, 280. And where we performed, and this platform completely was successful in receiving our customized and optimized network. But we want to do more. We don't just want to stop at kind of style transfer. As you know, we want to do phase swapping. This creates further complexity in our process. Phase swapping that use GAN have more parameters. Here are two examples: SIM swap with 107 million parameters, 56 gigamex, and phase shifter with similar or worse kind of numbers. There are in literature some attempt to go down, even in this case, even for phase swapping, in terms of complexity, but some recent work reach around 75 million parameters and 10 gigamex, which is still too high to target a microcontroller as the ones that we are targeting. We want to go lower than 2 million parameters and lower than 0.1 gigamax. So this is really far from our goals. We are around 200 orders of magnitude to go. So what is our proposed solution? We started from one of the very first phase swapping gun, the FG gun, which is simpler, effective but simpler, because the decoder can only generate one target identity. And then we worked on that. What we did is replacing the coder and encoder of this GAN with our Phinets, of course. And also we modified the approach to be fully convolutional, so to be better efficient on a microcontroller. What we do exactly? Of course, the FG GAN just work with 1-to-1, okay? So what we did, we trained initially two networks, one from me to me, let's say, from me to me, and one from Nicolas Cage to Nicolas Cage. I'm mentioning Nicolas Cage because the demo that I will show is about him. But this, of course, is not sufficient for a scenario like a smart city, because it's not only me going around in a public square, okay? So we modified first by training instead of a data set of just me, a data set which has more faces. We used the VGG face data set. And so that we had a network being able to recognize more faces, more general, let's say. Then we use a discriminator to discriminate, to understand where the fake face and the real one. And we swap, as it's maybe, I don't know, clear here. We took we took the, we mixed the decoder and the encoder of the two networks that we trained, and we used then the discriminator as a loss to train the phase swapping network. This is just to show you that this is the final architecture of our customization for the Kendryte. As you can see, we started from the specific characteristic of the platform that we had at our hand. So the platform has 1 megabyte of flash, 392 kilobyte was what we wanted to use in terms of RAM, and we wanted to stay around 63 million MAC. This is mapped through our equations that regulates the Phinet to 3 numbers in terms of T0, alpha, and beta, which go directly shaping the number of filters, the width, and the architecture of our network. We did it both for the encoder and the decoder, as you can see, with the different parameters down there. Okay, then we had to bring the model down to the microcontroller. So we needed to quantize the model, the network. And of course here we had another problem. The quantization of GAN is difficult. A small error is easily propagated in a high instability of the network. So to do so, we applied partial quantization, which is something that I heard also yesterday on FOMO. Maybe you use it. We kept the last layers in floating point, where the errors is a bit, propagates in a less harmful way. So this is what we had. Sorry, I'm not very good in using the pointer. Anyway, in the first picture, it's easier like this. You see what we had before doing tricks and tips on the quantization. I can, yeah, sorry. So here you have the picture of Nicolas Cage, which is very bad. You cannot even quite recognize him. Here we don't do no partial quantization. And also here we kept the strided convolution that were naturally there. So we first passed to partial quantization, and then we substituted the stride convolution with max pooling mainly to downsample the image with less, leading to less numerical instability. Of course, this costs a bit in terms of latency because we have more blocks to pass, but this is very small. Is a very small increased latency. We calculated it's less than 3%. With a huge increase in generated image quality. As you can see, the other picture is very recognizable. Why we wanted that people is really Nicolas Cage with the quality of image, because as I said at the beginning, we don't just want blurring the faces, we want to keep the expression. We want to keep the emotion of the person in a certain environment. That's why we put a lot of attention on this. Going to the end, these are the performance that we had in a comparison between what you can do with a SIM swap, of course, on a GPU, in terms of number of parameters and number of max. What you can do with the FGGAN, from where we started our modifying process to go to our generative network. You can also see the feed, which is a figure of quality of the image, which is better when it's lower. Here you see that we increase a bit in this. But I think that this is repaid by the fact that we are able to reduce the number of parameters of the 99.2%, the 98.4% in terms of number of operation, and we are anyway continuing optimizing this network to improve also and to minimize the loss of performance. I lied to you saying that we had finished our process because, of course, since we want to substitute the face of people inside videos, we need also to identify the face of the person that we want to change the face. This is done with a 4-step process. First, we detect the face. Here we applied again our Phinets, first version plus YOLO. Then we do landmark detection and face alignment. We do this using, in both cases, Phinets plus PFLD, which stands for Practical Face Landmark Detection. Why we used YOLO in the first step? Because it's the standard here, and because we already worked on that and optimized our Phinets to work with YOLO, which is what you will find in that paper that I mentioned before. Why we used the practical FLD? Not a real reason. We tried something, this was working, so maybe this can be also even optimized. Anyway, of course, the last step is face generation and swapping with the Phinets GAN. So here is the overall result with considering also this step. As you see, we have with only the step of face detection uses just 27K parameters, 6 million max, and 122 kilobytes of RAM. The landmark detection and consumes 4.1 millijoule per frame. The landmark detection instead is 64K parameters, 11 million MAC and 188 kilobytes per RAM with 7.3 millijoule per frame. So here we have a very nice kind of resource usage. Face generation, as expected, cost a little more, but still we have very good results because here we have these numbers that are here, 984K parameters. If you remember one of my first slides, it was that we wanted to target 1 million parameters, so we are there. 62 million MAC And even there, we match our target, and 392 kilobytes of RAM. With an energy of 34.3 millijoule per frame. So overall, we consume 46 millijoule per frame on this platform that we targeted, which means in terms of frame per second that we can reach this 6 frame per second speed at 280 milliwatt. Of course, we can play with this if we want to go down with the frame per second, and I'm saying this because in the case study that we have in the project, we have cameras working at 2 FPS, so we are completely in line with that. We can go a little bit lower in terms of velocity and then tuning better the consumption and other parameters and optimize depending on the case that we are addressing. We are keeping, trying to go on. Of course, we targeted in this example this platform, but as I mentioned, our approach is done for targeting any kind of platform, so we could even target other microcontroller that you know. I invite you to see the demo. Maybe some of you already visited our demo or poster and met Alberto, which I asked him to pass with the demo and give you the chance to do it online now, if you want. So if you want to be Nicolas Cage for a second, especially women, I don't know if they like it, you have the chance. The demo is passing through. And thank you for your attention. For more information, here are my contacts and the contacts of Alberto. Pass by our poster, our demo, and ask everything to Alberto, which is better than me in answering all technicalities and small details that you want to know.